Week 14, Part 5. This is on resolution of optical systems. So here's what we saw before. When you have a single slit and it's narrow, you start getting a weird effect we call diffraction. And as the slit gets narrower, the spot spreads out wider and wider in kind of a surprising way. But if you remember from the ripple tank examples, you could see how making a tiny slit like this would make the waves spread out more broadly. And as the slit got wider, then we had more of a concentrated pattern in the center. And then there's these funny little ghosts off to the side. And we had a formula that could calculate where the first minimum of that pattern fell. Now I want to talk about what happens in more typical optical systems. We don't have slits. We tend to have apertures that are circular, not line-like. And so what would happen in that case? Well, you might kind of guess, and you'd be very close to right, that if you have a circular aperture like this, so this is the opening, then the screen will show a pattern something like this. Now, once again, just like up here, the pattern on the screen is not just a geometric effect of the shadow of this thing. Because remember, when this gets smaller, that one gets larger. This is all a very tiny effect that you only see when these slits over here are in fact quite small, so that you see the effect of this spreading out. Small, they have to get down to the size of the waves involved, and then you start to notice it. If they're way larger, then you just don't see this effect, and what you get is more like you'd expect with just simple shadows or something like that. If you have, you just expect straight line travel over the waves. Now, once again, though, here, so with a circular aperture, you get a kind of circular pattern like this. But as this aperture gets smaller, this pattern grows. Now, it won't be like this. If you have an aperture that big, you'd never see this effect at all, unless you put a lens in it. But the pattern you'd get from something obviously this large would be tiny. So this is sort of a magnified view of what you might get from a very small hole even. The center portion of this is often called the airy disk, although I've also seen that used to refer to the whole pattern, but I think it's supposed to refer just to the center disk region here. And you can see it looks very much like what we had up here. You've got a large center maximum, and then a minimum, and then a sort of a ghosting. In this case, it's in rings rather than in little spots, but it's the same idea. The dimensions are slightly different than you might expect. You might expect the width of this would be the same formula as the distance to that one, but it has a funny little factor in it that's just slightly different. Now, what's this got to do with optical systems? Well, it turns out this affects everything: cameras, telescopes, microscopes, and everything. So here's an example of a very simple optical system. This might be sort of like a camera where you've just got a lens focusing things down to a point. Let's imagine that these are rays coming from some distant object that's just a single bright point, and we want to focus that down to a tiny image. And if this is even a star, so that it really is a very tiny object, but is putting out lots of light, tiny from our perspective anyhow, then we'd hope to focus this down to a nice infinitesimal point. If we could make our optics somehow perfect, get the shape of the lens to be just right. But it turns out it doesn't work that way. You can make the optics truly perfect in the sense that you get the curvature of the lens just right, so that all these rays you think would be converging on one exact point. And then when you look carefully at that spot, you will find, in fact, that if you magnify it, you'll see, oh, here's this pattern again. And it's the same pattern as we just saw. It's this airy disk surrounded by rings. And that comes about, again, because of the aperture limit. And you wonder, well, where is there an aperture here? Well, the lens itself is the aperture. And you can use the size of that aperture to determine the size of this pattern in the very same way. That then has an effect on resolution, on how fine a detail you can see. Clearly, if this pattern is larger, it sort of fuzzes out the detail. And we define resolution in this case by how close two things can be and still be seen as two distinct objects. So here's a case where now we've got two objects, maybe two stars, a red star and a blue star, the way I've drawn the rays here. And they would each be ideally focused to a point on the screen or on the image sensor. But in fact, they're each producing these airy disks. And so then the question is, how close can they be for us to still see them as two separate objects and not simply merged into one brighter blob that we wouldn't be able to tell was really two? To answer that question, you have to look carefully at what happens as these two come closer together. And people have studied this going all the way back to Lord Rayleigh, who first proposed the criterion that is usually used, though it's not, it's a little bit pessimistic. You can do a little better, but this is so easy to calculate. His criterion was to simply say, well, here are two objects that are pretty easy to separate. Down here, you'd say, boy, that looks an awful lot like just one blob. How would you know that was two stars rather than just one? He said that the limit is when one of these is sitting right on top of the minimum, the closest minimum of the other one. So take a look at the closest band here and finish the circle out from that one and go all the way around. And when that circle would pass right through the other one, and of course, when this one's minimum circle would pass through that one, that's when you're sitting right at the limit. And so if they're closer than that, you can't tell them apart. If they're further than that, you can. And as I say, this is actually just a little bit pessimistic. You can probably do a little bit better than this. And in fact, experiment has shown that people, in fact, can. But this is a simple limit, and it can be explained very easily theoretically like this, the basis of it. And this limit comes out to be simply 1.22 lambda divided by d. So it depends on d, the size of the aperture, the diameter of the aperture, which would be the lens or the mirror or whatever is the collecting object that sort of defines the size of the instrument if it's a telescope. For a microscope, it would depend on the objective lens, the effective diameter of the objective lens. That's a little harder to define. But so you need that diameter, and it also involves the wavelength of the light. You take the fraction of these two, and that gives you an angle. It comes out, by the way, in radians. Since this is a lambda is a wavelength, that would be in meters, and the diameter in meters. You come out with meters divided by meters. That's an angle, but expressed in radians. So that defines then the angle, the closest angle between two objects. You have to think then when you aim your telescope at these two stars, you have to figure out, well, what angle are they separated by, and that's what this is relating to the parameters of your telescope, the angle between those two objects in the sky. If they're actual physical things, say closer, two objects on the Earth, you would again have to say, well, how far apart are they and how distant are they? And from that, you can compute the angle between them and then relate that to this Rayleigh criterion. Next, we'll do some examples.